Yep. Thank you. Thank you for the reminder. Okay. So the co-channel interference will be lower if the cell where you reuse the frequency is at a larger distance. Okay. And that is possible when you have higher number of cells in a cluster. Okay. Instead of 7, if you had 12 cells, then of course, I mean, you could have another layer actually. Okay. And so the cell where you repeat will be at a even larger distance. And that's how your CCI will be lower. Now, this estimation, okay, how I mean, using cluster size or using frequency reuse factor, when you make, then of course you indicate your CCI, and we'll demonstrate a quick calculation for this purpose, where we assume some regular cell distribution. In practice, let me tell you, the cells are never this well organized. Okay, we have the same cell size for each of them, and the cluster size is also same. We're just repeating the same clusters. In reality, the location, I mean, the terrain, the distribution of different users, okay, the type of users, and different things affect the location of different buildings or other structures. Different things affect the radio network planning, and you may get different shapes for your cells, and the cluster size can differ. So the whole radio network planning is a complex job, and that has a lot of irregularities. But this regular fashion can be a good way for the initial explanation. Okay. So we are assuming here this sort of, and I probably told you before that we are not considering circular cells. We are assuming that we have a base station at the center of the cell, and that base station has an omnidirectional antenna, so it radiates equally in all different directions. So the coverage should be circular for a base station, or the cells should look circular. But the reason people don't draw circular cells when they show a cellular coverage is that if you use circular cells, then you either, I mean, you show holes and overlappings. Okay, so this demonstration is a is ideal. Okay, I mean, you fill up all the whole area without allowing any holes, and you also don't show any overlapping zones. Okay, so this is why instead of circular, people show hexagonal cells. Okay, but in fact, they are circular and they are just overlapped onto each other. Also, there is no clear demarcation for the circular area. Okay. Anyway, this network radio network planning, okay, which is called RNP, okay, radio network planning, or RNP, includes some trade-off, and we'll discuss them. Say the cluster size or the cell size. Okay, I already touched upon the trade-off for cluster size. Okay, for cell size, I mean, for cluster size, I say that as you increase the number of cells, your CCI will be lower, but the frequency chunk will be smaller. So each cell will get a smaller frequency chunk. So the capacity will be lower for each cell. So that is the key trade-off for cluster size. For cell size, you also have a trade-off. If you, I mean, here actually depends on how you view the whole situation. I mean, your viewpoint, what you consider constant. Okay, so the way we have considered here is that we are covering a particular area, okay, using cells. Now, if you have smaller cells, okay, then you uh, you have more resources available for the users, because I assume that uh, the area, like how I okay, one way to explain it may be, say you consider that in board budget area we have uh, 1000 users, estimated number of users is 1000, and you set up one base station there, uh, and we from one base station you have certain frequency, like say uh, maybe say 5 megahertz. Okay. So you are transmitting using 5 megahertz from your base station, and that is good enough for 1000 users. Okay. Now over time, the number of users increases, and it has increased to 4000. Okay. Now you don't find this capacity, or your available resources no longer sufficient. Many people will attempt to make calls, but they won't be able, because the frequency resources are already allocated to somebody else. Okay, so the frequency resources will be too much occupied or crowded. Okay, so a lot of times people cannot access, people don't get the resources. So because of the higher number of users, now uh, you face difficulties. So what you do, you split the board budget into 4 parts and set up 4 base stations. I mean, you add 3 base stations. Okay, so now you have 4 cells in the board budget area instead of 1, and each of the cell is again allocated 5 megahertz. Okay, because I mean you have 5 megahertz which you can allocate to each of the base station. Now you see the whole geographical area is split into 4 smaller cells. Okay, previously one large cell was covering the whole board budget area. Now you have 4 smaller cells, and then each small cell again has the same capacity, or I mean frequency resource, to support say 1000 users. Okay, so in 4 cells they have now 1000 users in their coverage area, and they can support these 1000 users using their 5 megahertz. Okay, so this way you actually get more resources now available for the user. Okay, so you actually increase your capacity. In other
That's the
words,
main reason of
more
cellular division.
radio resources are available for the users. So
Sir,
that has been possible because of smaller size. Okay, so
Hello,
sir,
sir.
is it,
uh, this is the
sir,
basic technique for the operators to improve the capacity. As you, yeah, please go ahead, Tasin.
So can you hear us, sir? Can you hear us?
here
Tasin,
you were
I don't
asking.
hear you.
Hello.
Sir,
Are you saying something? Not sure what's happening. Yeah, no, I don't hear you. You can hear me fine, right? Do you have any problem in hearing me? Could you hear me so far? You could, right? Oh, oh, I'm sorry. Yeah, yeah. Okay, sorry. My sound was turned off. I didn't notice that. It's okay. Now I can hear you. Say something.
Understand.
Yeah,
Yes.
okay. Yeah, Tasin, did you have any question?
So actually, I had a question actually.
Yeah, okay, go ahead.
So if a cell phone company takes 5 megahertz as their frequency from the government, and they can reuse again and again if they set up more base stations. Is that the main purpose of setting up more base stations and setting up more uh, cells in the area?
Yeah, yeah. I mean, in our example, in our recent example, we have considered that you can reuse the frequency in the adjacent cell. Okay.
Adjacent to the-
Yeah, yeah. So that is actually possible in 3G and sometimes in 4G too. However, in the case of 2G, it is little different as we were showing earlier. Okay.
Mhm.
But
Yes,
the basic
overlapping of
yeah, but the basic concept holds true that as you have a smaller cell size, okay,
Mhm.
that will be true even for 2G. Like in 2G, say if I reduce the cell size for all of them, right? For all of them,
yes.
then instead of here you see the uh, number of clusters to cover certain area is 4. Using 4 clusters, I'm covering this
The whole
whole
area. Yes, sir.
area, a certain area. Okay. So if I reduce the cell size, say if I make the actual area coverage for for every cell uh, reduced by half, okay, then what will happen?
There will
In
be
this
8 clusters in that.
8 clusters, right?
Yes,
So 8 clusters in this cell. So in that case, I mean, you have actually double capacity.
double capacity. Yes.
All right. You have again the same, every cell has the same frequency chunk, but with that frequency chunk, it is covering a smaller area. And in a smaller area, you have fewer users.
Yes.
So for every user, the radio resource increases. Okay. So this point holds true. I mean, I was trying to explain it using the board budget area. As you split certain area and use smaller cells. Okay. So the key advantage for smaller cells is that you have more radio resources available for the users. Now, the key disadvantage is that you need higher number of base stations. Previously, you had only one. Okay. Maybe you have to spend $20,000 for each of the base stations, and you add 3 more. Okay. So imagine how much costs you add. Okay. So you have higher number of base stations with higher cost. But with that, you can increase your capacity. So the first points for in advantage and disadvantage are the actually key points. Some additional points I have added here, but they are not much important. Like the second advantage here, uh, just to actually give you the idea that this type of changes are there. Okay, like less transmission power is required for the base station and the EV. Okay, but this is not a I mean, this is not a great achievement. Like now you see the total power in downlink is not less because you have now 3 base stations, 4 base stations in our example instead of 1. Each of them has now a smaller coverage area, so each of them will be transmitting at lower power. But the total power from all 4 is not like before. Actually, ideally, it is as much as you had before, right? In the downlink, you are not saving power. However, in the uplink you save, the EV has to transmit at lower power, okay, because the base station is closer, it can communicate covering a smaller distance, its transmit power will be lower. So you save some power on the EV end, okay. But nevertheless, it's not a big deal, okay. Now, then also on the disadvantage side, we have two other points which are not that important. Like there will be higher number of handovers. As you have handover means you switch from one cell to another cell. Okay, so if a voice call is up, you are hooked up with one cell. So radio resources will be allocated from this base station. As you move to the next cell, of course, the new base station has to allocate you the radio resources, and the old cell will take away its resources. So this is called handover. You're handed over from one cell to another. As you increase the number of cells, I mean, as you reduce the cell size, you'll experience higher number of, I mean, every mobile user, the users who are moving, will experience higher number of handovers. It's I don't mean to say it's a it's the reason I say that it is not much important. In the 2G days, you had few packet losses when you have and you have a handover. Okay, invariably there are some packet losses, but that could also be sometimes you could actually take care of that. You could retransmit the packets. Okay, so I mean, ultimately at the application layer, you may not have losses. But in 3G and 4G, it is possible that you actually overcome the losses even at the lower level of communication. Okay, so it's possible that you can avoid any packet losses in the case of handover. So frequent handovers may not be a problem, although you have some extra processing at both network end and at the UE end. Some extra processing will be there, but it's not a big deal again.
So, sir,
The third one, go ahead.
packet loss was more in 2G or is it more in 3G?
In 3G, you can completely avoid packet losses.
Okay.
Okay, we discussed that in cellular communication course. I mean, in 3G, soft handover, something called soft handover is facilitated, where you first make connection with a new cell, then you break connection with the old cell. So radio resources will be allocated from a new cell, okay, and then you release radio resources from the old cell. And there will be short period when you have connection with both cells. Then the same data will be actually communicated over the both cell links. Okay, so it is little luxurious, but you can avoid any packet losses. Okay, however, in 4G, people have again gone back to hard handover. Okay, in hard handover, you break and then you make. Okay, you tear down the radio resources in the old cell, then you create connection or establish radio resources in the new cell. So both in 2G and 4G and also in 5G, it is hard handover. Only in 3G, there is soft handover. Okay. You may argue that there will be problem in 4G and 5G. In 4G and 5G, some additional features are there, which can allow you to avoid any packet losses. Okay, although it's a hard handover. But we discuss these things in detail in the cellular communication course.
So, sir, in this 4G, there is more possibility of packet losses.
No, it is not. I don't mean to say that. It is not.
Okay.
It can avoid packet losses like 3G, but using hard handover.
Okay, okay, sir. All
Okay.
right.
Okay. I mean, in 2G, only in 3G, soft handover is there. Okay. And the purpose of soft handover, the reason they went from hard to soft handover is just to avoid packet losses. There is no second reason.
Okay, sir.
Okay. But in 3G is the soft handover is luxurious. Okay. Or I mean less frequency efficient. Okay. So people have gone back to hard handover in 4G, but adding some features to avoid packet losses. Okay, and there is a third point we can see in the disadvantage. Radio network planning becomes more complicated as you have a high number of cells. Of course, you increase the number of cells, so things will be more complicated, but that will be the job of the RF engineers. Why are they hired? Okay, they have to resolve these issues. So it's not again a big deal. Okay, so the key point here is the first one. Okay, the main drawback for a smaller cell size is the costs for more base stations. Okay. Now we'll discuss the trade-off for cluster size, and as I said, I actually already covered the main points here. Okay, when you have, well, it is similar. Okay, it is similar. It depends on how you look at things. Okay, what things you keep constant, and like when we are discussing the cell size. Okay, we consider that the same area we are covering. Okay, so anyway, here if we have smaller class is, I mean, the cluster size is smaller, meaning that you have fewer cells in a cluster. Okay, then of course every cell will get a larger frequency chunk. Okay, or you have more radio resources available for the users, so you increase the capacity, but the co-channel interference will then be higher because the cell where you have frequency reuse is now closer. Okay. Now we can see a second advantage for smaller cluster size. But I need to actually explain it. Well, let me give you an example for the purpose of explanation. Say we are designing a dormitory, okay, for our new students at IoT. So if we allow, say, 10 washrooms for 100 students, okay, and I mean this is considered sufficient. Okay. Now, what do you think if I increase? Well, I mean, what I mean that in a floor we have 1,000 users, and we are um, setting up 10 washrooms for them. Okay. Let's consider 100 users and 10 washrooms. Now, if the floor area is made larger and we have 500 users in a floor, okay. So, how many washrooms should be there in this floor? What do you think? For 100 users, we find that 10 washrooms are sufficient. For 500, how many should be
50,
sufficient?
sir.
50.
50. It sounds like that, but in reality, it may be only 30. It may be only 30. It's because the way people use the washrooms is actually probabilistic fashion. Okay, there is a probability distribution. Okay, so I mean, everybody doesn't need to go there together, right? I mean, for 100 users, why you set up 10, not 100? Because everybody doesn't go there together. So the way they go, it's actually it's a probabilistic fashion. When someone needs, he goes. Okay, somebody else needs, he goes. So it's actually probabilistic fashion. So when you increase the pool size, instead of 100, when you make the pool size 500, then because of probabilistic uh, I mean fashion for them to use, fewer washrooms will be sufficient. Probably you can, I mean, I'm using examples so you can visualize. Probably you can, right? Just think about the situation. Okay, so fewer washrooms should be sufficient. Do you agree?
Yes, sir.
Yeah, okay, probably. So the purpose of example, and there are some theories also. Okay, so with probability distribution, there's something, but I'm avoiding the theories here. Okay, so probably, I mean, intuitively you can understand. So this is how, as you increase the pool size, you need less resources will be available. Similarly, the uses of wireless resources is actually a probabilistic demand from the users. Everybody doesn't want to make call together. Some people makes a call, somebody else makes a call at some another time. Okay, so it's actually not, the way people make calls is a probabilistic distribution. The way people go for using some data application is actually probabilistic distribution. So that is why the resources you need will be lower as you increase the pool size. However, you can of course consider the, I mean, on the average requirement. If you look at usual requirement for washrooms or usual I mean average requirement, okay, or the requirements most of the time, then the way I explained will be actually justified. However, if you look at the peak demand, if it is like at the morning, everybody wakes up and everybody needs to go to washroom, most of them, okay, so these are some peak periods, then of course the resources, the washrooms may be found insufficient as you go that way. Instead, you don't increase the washrooms linearly, okay, as you cut down the number of washrooms, then at the peak demand moment there will be some difficulties. However, engineers have to work with an efficient solution. Well, as an engineer, you gotta understand that when you join the workforce as an engineer, your job will not be to provide the perfect service to the users, okay, or the best service to the users. Your job will be to make sure that your company make the most profit. They make the best revenue, okay, because it's all about money. Your boss
Yes.
or the company owner will be happy with you when your design, okay, gives him better money. Okay. So your job is not to provide the best service to the customers, okay, it will be to make your boss happy. And how you can do that? You can do it using a balanced or optimized solution. Okay, so the number of, say, if I still go back to number of washrooms, it may be, say, for peak hours, 30 may be little, may cause little trouble. So maybe you increase it to 35, but don't increase it to 50. Okay, so at peak hours, some people will get some difficulties and they may not take it seriously because at other times they don't have problems. So only for that short period they have some problems. Maybe they will take it gracefully. So that way. So you provide some interim solution or a balance between cost and quality of service. Okay, so a balance between them which can um, give you, I mean, which is more optimized in both senses. Okay, so but of course you should calculate the ratio, okay, between your peak demand and the average demand for your solution. Okay, so it is called OBF or overbooking factor. Now, as you increase, as I said, that as you increase the pool size, okay, your overbooking factor will be lower for the same resources. Okay, will be lower. I mean, or in the other words, keeping the same, to keep the same overbooking factor, you can reduce the resources. Okay, so you can actually, so that's an advantage.
Sir,
So
can
now,
you repeat this part again, sir? At the OBF part, sir.
so OBF is like, say, I mean, in the case of say washroom example, there will be some average demand that you can actually calculate for the situation. Okay, maybe it's up to you how you take the method for calculation, but what the average demand is. Okay, so so maybe the average demand is 30. Okay, but the peak demand is 40. Okay, for those 500 people, but so this OBF will be 40 by 30. Okay, but now if we increase it to from 500 to 5,000, what do you think? As you increase the pool size, the larger the pool size, your OBF will be lower and lower. Okay.
Oh, yes, sir. Yes, sir.
Your
Yes, sir.
OBF will be lower and lower as you increase the pool size. Okay, so meaning that when your OBF is lower, the resources that you need to provide will be lower. Okay,
Yes.
you can make things. So when you actually use a smaller cluster size, okay, you have it's like actually large cell size. However you look at it, I mean, it means that you smaller cells cluster size. Okay, let's take it this way: small cluster size. So you have more people in the area. Okay, so the overbooking factor is lower for them when you are covering more people in a under one base station. Okay, so overbooking factor, as you take fewer users in your coverage area, the overbooking factor increases. Okay, but anyway, I mean, in terms of cell size, if we consider, then the cell size is getting smaller and smaller. Well, every operator starts their business with large cell size, very large. Okay, like if you think of the very early days of our operators when they started operation, to cover the whole Dhaka area, they had just 4 or 5 base stations. So imagine how large the cells were, and that was sufficient because the number of users was very small. Also, they didn't have enough money to, I mean, there's not much revenue. Okay, so investment was difficult. So as the business grows, the number of users grows. So you need actually more base stations, or you need a smaller size, cell size, and you also start getting more and more money from, I mean, as revenue. As the business grows, from the users you are getting money. So this money you can invest to set up the new base stations. That's how every cellular operator sets up their business. Okay, they start off with very few base stations, so money starts coming in, and they use this money to set up new base stations. Okay, so, but these things are very tricky, very tricky. Okay, let me tell you that Bangladeshi people or Bangladeshi business people. I mean, there are very good business people in our country, but they cannot cope with the tricks that you need, okay, or the policies or the complexity level for business of cellular operation. All the successful cellular operators are owned by foreigners. Okay, Actel was there. I mean uh, uh, I mean the early form of Robi, Abul
Yes.
Khair. He had a good share. He didn't have a complete share, but he had a good share in Actel. But he later realized that this business is difficult. He left this business. He sold it. So this Robi is completely owned by foreigners, Azieta and Entity Docomo. They are the owners. The Japan-based Entity Docomo and Azieta is mostly Malaysian. They are the owners of Robi. Grameen has most of its ownership percentage with the foreigners. Telenor, Norway-based Telenor, has 55%. Dr. Unis has only 12%. Only 12%. And actually the business is taken care of by foreigners. Okay. The rest, 88%, is owned by foreigners. Okay, very difficult. And
So, sir, all these
Teleton,
cellular companies, sir, are they all like can we call them multinationals? Since like this Uninor and the entity you have just told, like
yeah,
all
yeah, yeah, they're multinational companies, definitely, but multinational without Bangladesh as the nation.
Okay.
Their ownership is almost the whole ownership comes from foreigners. Okay, it's multinational from different nations, but I mean Bangladesh participation is negligible. Well, Teletalk is the operator owned by Bangladesh, and I mean if you just check its profit, okay, and it's ridiculous. It's ridiculous. Both service and I mean the government is just spending on it. Okay, every year huge losses you have. There is. Okay. Anyway, now let's do a small calculation. Okay, I mean this is a very crude calculation. It will not apply to your real life radio network planning. However, these basic concepts can be helpful for some level of understanding. Okay, so this part I am showing from the book of Rappaport. These A number cells are where we are repeating the frequency, or I mean we have, these are called co-channel cells, or where we have frequency reuse. Okay, so these cells are marked here by A. Now, from here, it is not evident what the cluster size is, right? Definitely there is some cluster size, but we are not showing with colors here this way. Maybe if you show only the just 7 number cells, okay, then you want to find out how the clusters are organized or what the cluster size is. Okay, so then you need some trick, and that we are showing here. What do? You start from one cell and complete your journey as you reach its co-channel cell, and you go every time along a line that is normal to the arm of the hexagonal shapes. Okay, so for example, from here, from this center A, you start, okay, go along this line and then count the number of cells that you have on the way. So this is 1 and then 2. Okay, then actually you need to turn towards left or right to get to the co-channel cell. So turn right or left by 60 degree, and then go again along the line normal to the arm. Okay, so again you know that you have to cover 2 cells to get to the co-channel cell. Okay, now the number of cells that you cover in the first attempt is called I. So move I cells straight and then turn 60 degree and then move J cells straight. So for us here, I is equal to 2, and after turning we go J number of cells, which is again 2. So for both I and J, we have the values 2. Okay. To determine the cluster size, you just use this expression, I square plus ij plus j square. So what is the cluster size here? Is the cluster size for this diagram?
So that was I square plus J square plus
Ij. I square
Oh, so
plus
sorry.
ij plus j square.
4 plus 4 plus 4, sir.
Yeah,
So,
12.
12, sir.
12 cells. So if you keep marking here, you can do it. Then you'll see that with 12 cells around, okay, I mean, use different numbers, say 1, 2, 3, 4, okay, number up to 12. Then for around every A mark cell number, the number up to 12, then you'll see you'll be able to fill in all the cells. Okay. You can validate that this is a validate this formula. Okay. Now we can check here actually. We know that the cluster size is 7. Okay. Now give me the values of I and J here. Start from any co-channel cell and finish at start from any cell and finish at its co-channel cell. What is I? What are the values of I and J?
So is I2 and J1?
Yeah. Either you can take I1 and J2 or I2 and J1, both are fine. So with 1 and 2, your value of cluster size will be what?
Sorry, 1 square plus 2 square plus 2.
7.
3. Yes, 4.
7.
7.
Yeah. Okay. So we have just validated the formula. Okay. Now we know that the distance between co-channel cell affects your interference, and we'll call it D. Okay. So if D is higher, your co-channel interference will be lower. Also, the cell radius can affect your SINR. Okay. By cell radius, we mean the position of the user, or the distance between the user at the cell boundary and the base station. Okay. Assume that you have a user at the cell boundary. He is called cell edge user. The distance between the cell edge user and the base station is called cell radius. Well, we are considering hexagonal cells. So we'll assume the location of a user at a peak. Okay. So the cell, I mean here R is the cell radius. With our assumptions, R is called the cell radius. Well, if the cell radius is small, then the user can easily get better signal. Okay. For large cells, the cell edge users will get little more difficulties to get enough signal. Okay. I mean, his received signal can be, you can more easily make sure that the received signal is higher or significant for the cell edge users. So R also affects your performance in terms of your desired signal. D affects you in terms of your interfering or undesired signal. Okay. So if D is higher, it is more problematic. And if R is lower, okay, if your R increases, okay, then you have more difficulties. And if your okay, maybe I put this way: if R is lower, then it is better. Your signal power should be better. Okay, so consider SINR, desired power ratioed with undesired power. So if R is lower, your signal will be better. If your D is higher, then the interference power will be lower. Okay, so that's also a better condition. So D by R, or co-channel reuse ratio, Q, can be indicative of your condition, how good the condition is in terms of signal, in terms of SINR. Okay. Okay. Now let's assume that this cell and this one cell, okay, with O at the center and B at the center, are co-channel cells. So we are going I number of cells to get to the cell marked A, and then turn 60 degree, and then cover J number of cells to get to this co-channel cell. Okay. As we get to the center of the next cell, it's a distance twice A, where A is the distance normal to the distance of this part, which is normal to the arm. So you cover distance twice A, and twice A will be root 3R, as you can see here. Okay. Now when you cover a distance of I number of cells, okay, this OA will be I times twice A, but twice A is root 3R, so you have I root 3R. Then AB will be J times twice A, or J times root 3R. Now D, you can calculate this way: OB square, OA square, AB square. Okay. I say that this is a crude relationship because in practice, you don't find the cells to be located in this regular fashion. Okay. There'll be many different shapes, and they will have different positions. Okay. So we are considering everything theoretical. Everything to be perfect. Okay, a theoretical radionator planned area. So in this case, our D can be calculated this way: OB square equal to OA square plus AB square plus 2A OA AB cos 60 degree. So from which, as you put these values, you get 3R square N. You get 3R square times I square plus J square plus IJ. But for this part, we have cluster size N. Okay, so it is 3R square N, or D square by R square is equal to 3N. So Q, okay, co-channel reuse ratio, is root over 3N. Okay, previously we talked about, we used the term frequency reuse ratio, and here it is co-channel reuse ratio. Okay, now the SINR, okay, at the edge of the cell can be calculated this way. It is also called carrier to interference ratio. Okay. The difference between CINR, the term CINR, SINR, C by I, is sometimes interchangeably used. They are interchangeably used, but they have some strict meanings too. Let me try to write down the strict meanings. When you say CINR, so give me a second. Then you actually use carrier to interference plus noise ratio, and the signal before modulation at the receiver, before modulation, can be used for the desired power measurement. Okay. So you haven't yet modulated the signal after reception. So you have your signal modulated on the carrier. Okay. So it's the desired power, but you have the signal modulated on the carrier power. If you measure the power level then and calculate the ratio between desired and undesired power, then you may call it CINR. On the other hand, if you measure it after the demodulation at the receiver, so you have stripped off the carrier. Okay. Then again, you will get desired and undesired power. You can calculate their ratio. But the desired power then may be called signal. Okay. The carrier has already been removed. So this time you call it signal. So it is called signal to interference plus noise ratio. The interference you may not mention, or the noise you may not mention, but when you really calculate the quality of signal, then you have to
Assalamu alaikum, sir. I think you are muted.
Thank you. So in the denominator, you may not mention both I and N, but in actual useful calculation, you have to include both of them. Okay, you have to put both of them in the denominator. Now, the desired power level, we can calculate this way according to one of our methods to calculate the received power. Okay, if you have the power level known for a reference distance d naught, then for another distance d, you can calculate it this way, where n is called the path loss exponent, which is 2 for free space for a pure LOS link, which is 4 for the case when you have a second ray, okay, direct ray and a strong second ray. So it is 4, but in other environments, okay, in the usual environment, n has some other values. It is called path loss exponent. So this way you can calculate PR. So if we consider the cell edge user who is at the toughest position, then this D will be the cell radius. Okay. So for PR, you need to use R at the place of D. Okay, so this is the carrier power. Now the interference power will come from a distance D. So for I, you can use this relationship. P naught times D by D naught to the power minus N. Okay. However, the interference will come from a number of cells around. Like you see in this figure, you have, okay, there are many different interfering cells, okay, at different directions. So there'll be interfering cells all around your cell. Here you have, you have 6 interfering cells around. So let's assume that we have X number of interfering cells around. So the total interfering power will be like this. Then C by I, if I calculate, okay, we're just ignoring noise here. So it will be, you divide.
So what does I stands for?
I stands for interference. Here I stands for interference. C stands for carrier power. Okay, interference power. I stands for interference power. Okay, so the total I will be X times this value. Now, if you divide this C and I, then you get this expression. So there's the value of our C by I, or okay, it is equivalent to SINR that we have used in Shannon's capacity formula. Okay. Now, of course, if you have higher value of D, then you have higher value of Q, higher value of Q equals to D by R. And that's indicative of a better situation in terms of interference. You have lower CCI. If you have higher value of R, okay, then the desired power will be adversely affected. You have lower Q, and then you have higher CCI. Okay. Also, I mean, it assumes that you have the same location here. I mean, when you consider here higher R, and you relate it to higher CCI, it's sometimes considered this way, that you have the same location or same distance for the interference cell. But if your cell edge user, if your cell boundary is larger, cell radius is larger, then cell user is located further, then the cell edge user will be located closer to the interference cell. Okay, you got it? If you consider the position of the interference cell constant, then as you increase the cell size, or as your cell edge user is further away from your base station, he will be closer to the interference cell. So anyway, higher R, lower Q, higher CCI, and higher N. Okay, this we already considered, will have actually lower CCI, but I mean our Q also increases as indicated by this expression. Questions?
Sir,
Yeah.
Oh yes, sir. When sir, if we go back to our N part, so where we use that IJ formula, sir.
Mm-hmm.
So we were finding the nearest co-channel, sir. Okay, if my cell is that cell number 7, that means my co-channel will be the other cell that is number 7, right, sir?
Right.
Okay. Answer. When we are saying the co-channel reuse ratio, sir, so what is the significance of it, sir?
It is an indication of the interference condition, okay, or the signal quality, how you are affected by. I mean, actually, it is an indication of SINR. Okay. How much difficulties you have in signal desired signal power, and also the interference. Okay.
So when we are saying interference is obvious due to the noise. So
yeah, I mean, you see, it is this ratio of D by R. D higher means better in terms of the co-channel cell is further, and R lower means again the desired signal is better, interference will be lower.
Okay, sir.
Okay. Now, instead of just cells with a single antenna at the center, we're considering the base station with a single antenna, and the antenna radiates equally in all horizontal directions. So we actually have considered omnidirectional antennas. But in most cases, you have sectorization in a cell. The antenna, the base station radiates in different directions, and the most common number is 3. Most commonly, you have 3 antennas on the base station radiating in 3 different directions. So a base station covers 3 sectors. Okay. Now these terms are vague. What you call cell, what you call sector. In fact, every sector here functions independently like a cell. Okay. So from 3G on, the sectors are called cells. In 2G, the area covered by the base station is called cell, and as you split, with different antennas on the base station, they are called sectors. But from 3G on, the sectors are called cells in 3G, 4G, 5G. And the whole area covered by a base station is referred to as something covered by the base station itself. Okay. For 3G, the base station, for every technology, 2G, 3G, 4G, 5G, the base stations have specific names. Okay. So it is related to a covered area from this particular base station. Okay. So if we have this sort of 3 sectorization, okay, in a cell, then let's use this example. We have 15 megahertz list from the government. So in total, we have 75 channels available. 15 megahertz divided by 200 kilohertz. So 75 channels available. Okay. Now we are using n equals to 4. The cluster size is 4. So the number of base stations, okay, use is 4. However, in every cell, okay, in 2G concept, the area under base station is cell. So in every cell is split into 3 sectors. So actually, you have 4 into 4 times 3, 12 parts. So the available spectrum will be shared by 12 sectors. So you have to split 15 megahertz into 12 components, or you have to split these 75 channels into 12 components. I mean, in 12 parts. Each sector will get a share of 1/12 of 75, but you need to get some even number. So, you know, I mean, each sector will get 6 or 7 channels, right? I mean, if you allocate 6 channels, yeah.
So can you kindly say different repeat what the sector is? It's like
Yeah.
sector.
So previously, our cluster size concept, okay, did not have sectoring.
Yes.
So the calculation was easier. You have, say, you split the whole frequency spectrum available into by the number of cells. But if you sectorize, if every cell is again split into number of sectors, then what do you need to do? The spectrum has to be actually split into higher number of chunks. So you can allocate every chunk to every sector, right? Sectorization actually
Yes.
splits the spectrum into more components. Okay. Now in our example, the cluster size is 4, only 4, and every cluster, every sector is split into 3 parts. 3 sector cells you are using. So in every cluster, you have 4 cells, but each of the 4 cell has 3 sectors. Okay. So each of the 4
So
cells have
each cell is made up of 3 sectors. Right? Each
right.
cell is made up of 3 sectors.
3 sectors.
Okay.
So it is like this. Okay, I should have shown this graph, this figure actually. I mean, I showed it, but I should stay on it more. So at the center of a cell, you see the red mark, the red dots represent base stations. And the base station uses 3 antennas in 3 different directions. That's how they cover different parts. Their coverage area will be different. Now, each of these coverage areas from the same base stations, the 3 different coverage areas will be treated as different sectors.
Oh,
Okay, will be treated as different sectors. So even in our example, you have 4 cells in a cluster, but every cell has 3 sectors. So in total, you have actually 12 sectors. in a cluster, meaning that the spectrum, available spectrum has to split into 4 times 3 into 12 components. Okay. Which you may also work out this way. So you determine the number of channels. 15 megahertz is divided by 200 kilohertz. So if you determine the number of frequency chunks available, 75. And among the 12 sectors, these 75 channels should be distributed. So each sector will get 6 or 7 channels. If you consider cells with 7 channels, then there will be 56 time slots. Okay, or 56 voice users can access resources or can be on calls. Okay, in a sector. You have 7 channels in a sector, but a channel, a 200 kilohertz chunk is time shared by 8 people, right? You also have TDMA on top of FDMA. It's time shared by 8 people. So every 200 kilohertz chunk, okay, will be time shared by 8 people. So 7 times 8, 56 time slots are available, or 56 users will be able to access together. Okay. For voice, you need just 1 time slot. For data, it can be 1 or more. Is it clear so far?
Yes, sir. Sir, is
Time
the
is
number
up.
eight-
Yeah.
Yes, the time is up.
fixed for TDMA?
So,
Is the number 8 fixed for TDMA, or
it is fixed. Yeah, yeah. This 200 kilohertz chunks, 8 users. Its length it is 4.615 millisecond. I mean, for every user, there is a period of 577 microsecond. Okay, all these numbers are fixed by specification. So every TDMA frame, every whole repetition of 8 users, okay, will be 8 times 5577 microsecond, which is 4.615 millisecond. So all these numbers are fixed.
So, sir, these are like 8 users can use that 7 channels in one sector simultaneously.
Right, right. Okay, we'll go from there. But do you have any questions?
No, sir.
Okay, we have a lab class today in the afternoon. You're supposed to install NYU SIM. Have you installed it? If you haven't, please install the software. I have already, you can download it, or
Yes, sir.
I have also,
open it.
yeah,
I don't know. I just followed the
it's also available in our Google Drive. But as you run the installer, it will download several 100 megabyte. Okay, maybe around 500 megabyte or around 900 megabyte. It will download.
915 moto.
Okay, okay. So you need to allow enough time. Okay, so if you haven't installed it already, please do it quickly. Okay, so I'll see you in the afternoon, inshallah. Well, by the way, I feel little feverish. Okay, from yesterday. Do you have any time slot free tomorrow? Then I feel like taking the lab class tomorrow instead of today.
Sir,
Do you?
I think the CRs can get back to you, sir, soon, inshallah.
Okay, okay. If I don't hear from anybody, then I'll assume that we are having our lab class today.
Okay.
Okay. So if you can manage any change, then please let me know. Okay, I'll see you shortly. Thank you for your time. Assalamu alaikum.
Assalamu alaikum.
Wa alaikum assalam.